Good morning, everyone. So today we have the pleasure to have with us Ulli KÖSTER. So just to say a few words about Ulli, he started to study the radioisotope production during his PhD in Munich. Then he got a CERN fellow at the ESOL facility at CERN and was then the coordinator of the TargESOL project for ISOL targets optimization. And since 2006, he works at the ILL Institute in Grenoble. And among the large variety of topics on which he is employed, he is responsible of the Lohengrin fission fragment separator. And he is also the coordinator of the ILL radioisotope production for medical applications. So today, Ulli will present a part of what he is studying, linking fundamental physics and medical application studies, with this presentation named From Nuclear Medicine to Nuclear Astrophysics.
First of all, thanks for the invitation. And I tried to adapt my usual talk about nuclear medicine to put it more in the jargon of nuclear astrophysics, which is in RESANET an important topic, and to make some comparisons which should maybe trigger some discussions. Moreover, I especially squatted the office of my son, who wants to become an astronomer, and you see behind here the telescope on the roof, the illuminated glass and wood. So now, if you wondered what was in the announcement with strange comparison, you will soon get an explanation, because I will try to find a lot of synergies between these two fields. Now, this is our galaxy, the Milky Way, shown in different wavelength regimes. And you see here hydrogen, atomic hydrogen, which is kind of the warm interstellar medium, clouds and dust. Then you have some infrared spectroscopy, which is interstellar dust, which is warmed by sunlight or starlight. Then you have visible, which is dust would then show up more shadows, and obviously the light of the stars. You have here the X-ray regime, where you see mainly hot gas, plus some shadows from dust again. And then we have here the annihilation gamma rays, which shows us that there's some stellar nucleosynthesis going on by fusion or by processes which are producing neutron-deficient isotopes like nickel-56 or 44 titanium or explosive scenarios. And then we have the possibility to look for specific radionuclides by putting a gate on a given gamma ray. And this is a very powerful method to understand better the universe. And actually, such multispectral observation has a similarity in medicine, because medicine is also using many different methodologies. So we have MRI imaging for seeing the hydrogen distribution, soft tissue. Infrared would show some differences in temperature, surface body temperature. Visible obviously shows the skin. The X-rays shows the bone structure. Then we will come to positron emission tomography, which will show the local accumulation of specific substances, or imaging techniques based on gamma ray emission of individual gamma ray isotopes, which shows also the specific accumulation of given substances. Now, nowadays, obviously, this is only different types of photon wavelengths, but nowadays we are speaking about multi-messenger astronomy. So we should maybe mention the gravitational spectroscopy, made be direct by gravitational wave detection, or indirect by the quantification of dark matter. Now, you might wonder, but actually this has also an equivalence in medicine, which is very cheap and easy and frequently used. And in this context, we should remember that not every fat man contains plutonium, but the collective cost of fat man to humanity could be actually higher than the fat man in history. And then we have other techniques which don't have a direct equivalence. Obviously, in medicine, ultrasound imaging is used, which is a very common, easy, low-cost method. You can even use Doppler to see relative movements, which in astronomy we do rather with optical spectroscopy by the shift of the emission lines. And it's clear why this is not being used as in astronomy. It would be very expensive to fill all the empty space with the ultrasound transmission jet. On the other hand, recently astronomy used neutrinos as messengers, and this clearly does not have an equivalence in medicine. So if your doctor tries to prescribe you a neutrino scan, be doubtful. And if your financial advisor tries to make you invest into this neutrino energy company, which is trying to sell a kind of solar panels which should absorb neutrinos and solve the energy crisis, be twice doubtful. Now, to make nuclear medicine, we use quite a diversity of radionuclides, but you see the diversity of radionuclides in a nuclear medicine sense is much more restricted than in a nuclear physics sense. That is was a few years back a near exhaustive picture of what is being used in nuclear medicine for different applications, and the size is a bit representing the quantity being used. Now, obviously, we need different types of emission because we are using different techniques. Here on the top, we have the imaging methods where single photon emission computed tomography will scan individual gamma lines, and positron emission tomography will use annihilation radiation. Now, just for the jargon, one can use the same type of camera either to look planar, a projection, which is a 2D image, it's called a gamma camera or planar scan, or you make it rotate around and reconstruct afterwards the 3D image, and that's and technically, you put a collimator so that you are sure that you are only detecting gamma rays coming from a certain direction, and detector, and you count scintillation light, or you have a solid state. And if you look what is the best energy for this, you don't want to have higher energies because then your detection gets less efficient and your punch through the collimator gets bigger. You don't want to have very low energies because then the self-attenuation in the human body becomes more important. So there's a kind of a sweet spot around 100 to 150 keV. And it happens that one isotope, or more precisely an isomer, happens to fall directly into the sweet spot, which is technetium-99m, which emits a 140 keV gamma ray with a high intensity per decay. It has a useful half-life to make chemical compounds, inject in the patient, and not too long so that he doesn't have radiation too long in the body when he goes home. And it is moreover easy to produce indirectly because you can produce molybdenum-99, which keeps decaying, producing technetium-99m. Then you use a technetium cow generator where the molybdenum is absorbed on a column. And whenever you wash through with a sodium chloride solution, you wash out the technetium, which is not bound to the column. And you can use such a generator for a week or so. So that is very important in nuclear medicine. Now let's have a look on the importance of technetium in nuclear astrophysics. When technetium, which does not have any stable isotopes, has been detected in optical spectroscopy, it was immediately clear that this is a direct evidence of ongoing nuclear activity in the interiors of the stars. So this discovery, beginning of the 50s, was already important contribution to the landmark paper of D²FH in 57. Now, about at the same time, there was a team at Brookhaven National Lab who has invented such a molybdenum technetium generator. So you see if it's written by chemists, that it's slightly sloppy. They forgot about the M here. But this letter actually was not even written by chemists. That was written by lawyers who was in the BNL patent office to study if it is worthwhile to patent such an odd invention. And they came to the conclusion that while this method is probably novel, it appears that the product will probably be used mostly for experimental purposes in the lab. So no further patent action is warranted. And we are not aware of a potential market for technetium-99 great enough to encourage one to undertake the risk of patenting the lab. So we see that this field, nuclear medicine, is extremely conservative because they get only interested when there's already a market, but they are not jumping on something which is really prospective and completely. Now, nowadays, and this was the image which we have seen, it is used a lot. It is used, for example, to highlight if there are bone metastases in cancer patients, because typically certain types of cancer in a later stage try to grow in bones, and it's very important to decide for the therapy action if this has happened already or not. It's also used for cardiac imaging, and if you think that those images look a bit blurry, then it is because it's not always needed to have the ultra high resolution to make the conclusion a quantitative conclusion. Basically, what you want to see here is blood flow in the right and left part of your heart. So it is not necessary to have the ultimate spatial resolution. And there's even an important application, which is more than 10% of nuclear medicine procedures in Europe, which is kidney scans. So if you have a doubt that one of your kidneys might be blocked or not working correctly, you give a radioactive substance and you check the time behavior, and this here is minutes, 2 minutes, 10 minutes, 20 minutes of activity retained in the right and left kidney. Here this is just for illustration. Basically what you do is you integrate over like one very big coarse pixel which represents one kidney and the other kidney. And what you would expect is that both have some uptake and then some elimination into the bladder, into the urine. And here you see clearly it's taking up, but it will never go down. So that is some kind of blockage. Or here it's going up, but then it's not dropping as quickly and it is saturating at a higher level. So basically you are only interested in the time information and you have no need of any spatial resolution. So don't believe that progress is only made by making better and better and better spatial resolution. Sometimes it's not needed. Sometimes you take just 1 pixel or 2 pixels. And if you wanted to just look out and there are no clouds and suddenly it gets pitch dark at lunchtime, you can detect and measure the duration of a solar eclipse. And you don't need any high resolution. Now, I told you that technetium is a very important isotope. It's nowadays like 80 or 75% of all procedures. And that makes more than 30 million patients per year, which is a tremendous scale. I mean, it is 20 petabecquerel, which is being injected, which is 0.1 gram of a radioactive isotope. So when you think, I have found a great method how to make technetium-99m with my Culex or whatever method, just forget it. It's completely, the need is completely out of scale of any lab experiment. So if you think and you are happy that you produce something which you put in front of your germanium detector and say, I have seen a gamma line of technetium, it is very, very unlikely that this can be scaled to the industrial scales needed to make a meaningful impact in the world. Now, technetium is not the only isotope being used. There are others, and for example, there here iodine-123, which can be used as it is here. It's basically used as iodide, which will highlight the thyroid. But it can also be coupled to other compounds, and often it can even replace technetium. And there is some list of certain gamma emitting isotopes. Now, how is iodine-123 produced? You are starting with a xenon-124 target. You make a P2N reaction, and then you let it decay to iodine. And then you can chemically easily separate the iodine from xenon. There's only one problem, and that is the very low isotopic abundance of xenon. Already xenon as an element is not very abundant, but the xenon-124 out of this is less than per mil. So it is extremely expensive when it is in enriched form, and it can only be used with some very special devices which have multiple safety margins and windows to not lose any of your expensive target, which costs 200,000 euros or so, 1 billion. Now, why is it so expensive? That is the curse that it is a p-nuclide. And nuclides are rare and they are expensive. So that is a direct consequence of the nuclear astrophysical production process leading to this xenon 124. Now let's go to PET. So you know all that's is positron emitters which are stopped in short range, and when they annihilate and you make the connection of the 2, 5, 11 photons detected diametrically opposite to reconstruct from many such interactions the emission volume. Now the most used is fluorine-18, has a reasonable half-life, high positron emission intensity, and low energy, which means a short range, high intrinsic resolution. You produce this with cyclotrons. There are more than 1,300 worldwide which are doing this every day, normally by irradiating oxygen-18 targets, PN reaction, and chemical separation and transformation into the compound that is used. Now again, it's a bit unfortunate, but the isotope of interest is not so super abundant compared to the dominant oxygen-16 one, only 2 per mil. So somebody could say, I will find a way out. I will use a different nuclear reaction where I can make use of this oxygen-16. So if I bombard this oxygen-16 with a helium-3 N reaction, I come to neon-18, which decays to fluorine-18, and I can produce fluorine-18. So great, very cheap target. You take water, distilled water. But the projectile is now very expensive because it happens to be the lowest abundant, relative abundant isotope on the chart of nuclei. So it's very unfortunate. Again, we fall into a trap that astrophysics left for us, that this helium-3 is very, very rare. Now, those were just 2 examples for diagnostic imaging, but eventually the patient doesn't want to know only that with a very good reliability that he is really, really ill. He's asking to find a therapeutic way out of his illness. So that's a bit like in astronomy. For a long time, astronomy was a purely observational method. And it's obviously very difficult to interact with that huge celestial bodies. And it was very recent that the DART mission has shown that one can deviate celestial bodies from their trajectory. And also over the last decades, it's due to our collective effort, we are trying to prove that humankind can even change the surface temperature of a celestial body. But those are 2 kind of exceptions. Usually it's a purely observational method. Now, in nuclear medicine was also for a long time mainly known for its capacity to pinpoint exactly the location of cancers and metastasis or so. But then you have to hand it over to a surgeon or to a radiation therapist to irradiate the cancer. But what do you do if you have patients which have so many spots, and here the dark spots are in a PET scan, the places where the radioactive substance is taken up. So that is just for historic reasons, they plotted in inverse, like a negative of a photo. And with exceptions, obviously, in this case of kidney or bladder, where the excess liquid is being eliminated in a natural way. So you see here, all the dark spots are metastasis of a cancer. And such a patient, even the surgeon or the radiation therapist cannot save, because the surgeon cannot cut apart a whole patient. He can take out 1 tumor, but location, but or 2 or 3, but not 50. And the radiation therapist, he can localize, irradiate from outside, but he cannot irradiate the whole patient. So different method is needed. And there is a biological way to address this, namely to make a systemic treatment. So you inject something, it goes around the whole body, and it tries to target the tumor. And the most primitive way is the so-called chemotherapy, which is just trying to target cells which are dividing more quickly than normal cells. So it has a certain selectivity towards tumor cells, but not such a great selectivity, and therefore you have a very small window between therapeutic efficacy and side effects. Now, if we find that certain cancer cells have a specialty, which means some kind of receptor on the surface, which can be selectively targeted with a biological vehicle, we can make use of this because this would now only go to the cancer cells and not to all other cells. But then we have to hope that this vehicle has some biological activity to kill the bad guy. So it's a kind of a biological 007. He has to identify the bad guy and kill him. And that dual capacity is not very frequently there with biological vehicles. But you can simplify by separating functions. So you tell to your biological vehicle, just find the bad guy and hold on him. And in your backpack, I put a radioisotope, which will take care of the killing. When you have now split the functions, you have much more choice of biological vehicles to do so. You can exploit small peptides, antibodies, and so on. Then you have to put into a boat chemist to make a stable linker so that your radionuclide stays always in the backpack and doesn't get lost in the way. And you have to choose the radionuclide, and that involves quite many disciplines. So it's a very interesting approach, but it's more complex. Now, for such a vehicle, you can put a radioisotope in for imaging, SPECT isotope or PET isotope, just to make sure that for this particular patient, your vehicle goes really to the right place before even starting the therapy. And afterwards, you switch and you put a therapeutic isotope, which is now either a beta emitter with short range, 200 keV energy, alpha emitter with even shorter range, and ultimately, but that was still in the development phase, Auger electron emitters, which would emit many electrons at a local spot. But you have to find a way to bring biological vehicles very close to the nucleus. This would make the highest standard. Now, here we see our patient again. And that was before he has undergone 3 cycles of treatment, where this isotope, it's a 1-week half-life beta emitter, was administered. And afterwards, the same image shows only the normal uptake and elimination process via kidney and bladder. So this was the first patient treated with such a new substance. And this patient had a very advanced prostate cancer, which today has no other meaningful treatment option. It was developed at the German Cancer Center in Heidelberg, published in 2015. And since there are so many cases of prostate cancer, the community immediately jumped onto this and made many, many clinical trials with hundreds of patients, which were extremely convincing. And this led to the approval. First of all, it led to many publications, and this is just to show you the explosion of publications once there is a new biological vector, which is really very selective and can be combined with the new isotope. And it led in this year to the approval of a new drug, which is 177 lutetium PSMA in the US, and it is expected that this will happen also soon in Europe. And that contributes to making this isotope really the gold standard for radionuclide therapy. You see here a drug which is picking up the lutetium-177, which we are producing at ILL in Grenoble, and brings it to an outside radiochemical lab for purification before it is being distributed to the hospitals. And you see even the truck driver has already adopted his number plate to make use of it. Now, a nuclear physicist might ask, okay, that's very nice. You have all these biologists working for you, but what can I do when I do nuclear spectroscopy? So what are the numbers which you need for me? And the first number, obviously, is to find the half-life, make your decay corrections and everything. So you look at the half-life of lutetium, and actually this had quite some history. So you see that old measurements were covered 6.6 days, then it went up to nearly 6.8 days, but with huge error bars. And then this became more and more precise until it homed in here at 6.75 days, basically determined by one experiment. And indeed, this experiment did show, and that was done at Strasbourg, so today this would be IPHC. This showed a very nice decay curve of the dominant gamma line of this lutetium, and they came up with a very, very precise number. Now later this has been repeated, for example, by IRMM in Gel, and you see also a very nice linear decay, but they didn't stop at the same time when they stopped the measurement, they just kept it running. And you see that suddenly it bends off, and actually it has, if you fit it now with two exponentials, then the short decay part has a very different half. And that was done correctly, showing residuals and so, which wasn't fashionable at that time. So you see that this number has a whopping systematic error of 145 sigma. And actually this group left quite a big trail in the field, because there are many other isotopes where they came up with such very precise numbers, which today are all contradictory. Now, why is this so that you have this slow component? That is because there are two isomers of lutetium, and the ground state, which we want to use, it is for 6.65 days. And then it has an isomer, high spin isomer, which lives 160 days. And when you produce by neutron capture on lutetium-176, you produce a lot of the ground state here, big cross section, but you also produce a little bit of the isomeric state. And meanwhile, people have understood this. They have found ways to make pure lutetium, and now all recent publications have homed in on this lower. And there were some intermediate ones which didn't decide where they want to put them. Now, this isomer is very interesting for nuclear spectroscopy purposes. It's basically the most complex decay scheme which you can have with a portable source which lives half a year. So if you want to try the analyzing power of your spectroscopy setup, germanium or lanthanum bromide, there's nothing better than this. We did recently so in Grenoble, and this made a nice publication on measurement of half-lives with the lanthanum bromide correctly gated with germaniums. But if you want to use it in a nuclear medicine department, it is just disturbing. Because when you want to saturate your cancer cells with radioactivity, you have to give more than is needed. And actually 80% of such peptides are eliminated within the first 2 hours via the urine. And so the patient goes in the nuclear medicine department on the toilet, and this urine is collected. And then you wait, whatever, 10 half-lives, 10 weeks, before the activity has dropped so much that it is below the free limit, and you are allowed to release it in the sewage plant. Now, if you have a small admixture of something very long-lived, this doesn't work anymore. And so that's a very important problem. Here's even a PhD which was made with simulations and measurement of radiation doses in the toilets of a nuclear medicine department. I show this mainly if your students complain that you make them simulate with Géant or MCMP too complex geometries, show them this and they will stop complaining. So now let's question, why do we produce this high spin isomer? Now, what I show up to now in black, because it's a near stable isotope, actually should have been shown like this, because we all know that odd isotopes are normally unstable. So there are only 4 exceptions, and the heaviest is nitrogen-14, and all odd isotopes above are unstable. They might be long-lived, like this one, but they are unstable. And you have here a low spin isomer, which will decay very quickly. And then you have here this high spin isomer, which has this incredibly high lifetime because it is a K isomer. Now, if you start out with a high spin isomer, it is no wonder that a small fraction of neutron capture will end up in another high spin isomer, another K isomer. And meanwhile, this has changed. So the isomer is now below, which means the ground state is the short-lived one, and the isomer is on top. And obviously, I let you read this up. That is a very interesting isotope also for nuclear astrophysics, because it was speculated it could be used as a cosmochronometer. But due to gamma-gamma prime reactions, which can make these two isomers communicate among each other, where you go up and then via doorway state you rain down to the other one. Actually, the lifetime in an astrophysical environment will depend on the abundance of gamma rays and the temperature, and like this, it is probably rather a thermometer than a cosmophonometer. Now, again, a caveat. So obviously, everybody has in mind, oh, there's a problem which we have to solve. And I have at home my MR12 spectrometer, or I have a laser spectrometer, and I'm very proud that I can separate isomers. So why not use it here? Let's imagine you have a market of, and that is expected for the coming years, 100,000 prostate cancer patients per year, which have to be treated, which means that you have to inject them with 4 terabecquerel of this isotope, which is like 1 gram pure radioactive substance. And again, it becomes clear that while theoretically possible for a tiny, tiny scale, in real life, it is completely out of scope to use lab methods of isomer separation to produce this huge quantity which is required. There's another way, because we could produce ytterbium-177. Now, this is the medium spin, but it decays exclusively to the ground state of the lutetium-177 and not at all to the isomeric. So what we do is we start out with ytterbium-176, we capture a neutron, and then we rely on the spin selection rules of nuclear beta decay, which will only populate the ground state. And this so-called indirect production has a second effect that we will not produce or leave in the target material any stable lutetium, which would dilute our therapeutic action. So we get a much cleaner product. And as a side remark, people say, oh, now there's a problem. We don't have enough reactors and we don't have enough irradiation positions where we make this neutron irradiation. I have this nice neutron accelerator, which I will use now to make a DP reaction to produce this. Now, the problem is that DP never comes alone. You make also DM. And with the deuteron, you bring in more angular momentum. So actually, you would produce even more of the high spin isomer compared to a neutron capture only. So it is not really competitive in terms of yield, and it would produce again lutetium-177M, which you can avoid by using some. Now, you might wonder how those images were made. I mean, here, this is a bit not so good image, but it's spec. Those high-resolution images were done with gallium-68, which is an easily available PET isotope. But obviously, the lifetime is not exactly the same. So if you want to measure exactly how it is taken up and eliminated, you can't see after a couple of hours. And chemically, they're also not exactly the same. So it is used in clinics, but people are thinking about something better. And those are so-called theranostic couples or matched pairs, where from the same chemical element, you are using an isotope which is a therapeutic isotope, and you have a diagnostic isotope. And like this, there's no discussion that it will behave the same in vivo. Now, lutetium doesn't have this, but let's see, for example, scandium. Scandium can be used for imaging, and it is actually used to replace gallium because it lives longer. So you can really follow after 19 hours where it is. And it is very well matched to this presently approved drugs because it can sit in the same chelator, the same cage, chemical cage, which is keeping this metal ions in place. And scandium-44 can be eluted also from a generator, from a titanium-44 generator. Now, here we have a link to nuclear astrophysics because scandium-44 line, this 1157 kV line, was detected by the Integral mission. And from this, one infers the location of titanium-44, which is the mother isotope of scandium. Now, how do they do this? If it would be just a positron emitter, you cannot localize so well, but nearly all positron emission proceeds via this 1157 kV level, which emits a prompt photon of this energy. And this prompt photon is used for a Compton camera. So here, COMTEL, you have an active scatterer and then a detector, and from this you can reconstruct the angle, and then you have a Compton cone, and then with one event you know with a probability where it is fair, and if you have many events where the different Compton cones overlap, you can localize. Now the same could be used with patients, where you would have a photon emission, you have a scatterer and then a detector, and you could localize this. And if at the same time you have a PET emission, then you would just need one event to cross your Compton cone with the line of response, which is given by 2511. You would need less and less activity to get the same spatial resolution. There are different ways to realize this with solid detectors, which is being studied in Munich, or with liquid xenon detector, which is being studied in. Now, if you have the scandium-44 for diagnostics, it has a matched pair, which is scandium-47, and scandium-47 can be produced in a non-carrier-added way, similar like lutetium, by irradiating one element down, calcium-46. You capture a neutron, you let the intermediate decay, and you separate once or several times, because it's so long-lived that it will build up again, the daughter nucleus. Very clean. It has been used by irradiations at ILL of this calcium-46, but there's a problem. Again, we are falling into a trap, but the most interesting isotope is extremely rare. I mean, that is in relative isotopic abundance, the second rarest on the chart of nuclides after helium-3, in total abundance even lower. So it's very unfortunate. And why is this so low abundant? Again, D-square FH tells us that sulfur-36, calcium-46, and calcium-48, there's no other production method than the R process. And if you want to understand why then calcium-48 is better produced than calcium-46, you have to look at the publications of Olivier Serolin, who has investigated the capture cross-sections here by the DP surrogate. And you see here, depending on the neutron density, you home in on the ratio which we find today. Now, there's another interesting combination of matched pairs. It's actually 4 different isotopes belonging to the same chemical element. That's quite unique. That is terbium. So terbium has a beta minus emitter, which is very similar to lutetium, but better, produced in large quantities in reactors. It has a SPECT isotope, which is terbium-155, with similar half-life. It has a PET isotope, which is even longer lived than scandium, 18 hours. And it has an interesting alpha emitter. Now, how would you produce those neutron deficient ones? Now, classically, one uses cyclotrons, one uses like 12 MeV protons, you make a PN reaction. So the only thing you need is a lot of enriched target material. And that is probably possible here. But here it's getting very challenging because it has, again, such a low natural abundance. You remember nuclide. So there was one demo experiment with the historic enriched gadolinium-152 target at the tandem accelerator in Munich, and a demo separation of gadolinium isotopes in Sidonie at Marseille. And this is a project which is now being followed up by Charles Olivier to show that one can really produce very high enrichment, enriched targets of gadolinium. Now, another completely orthogonal way to get to such exotic isotope is also given by astrophysics. There are some isotopes which all the normal paths, S process, R process, and so will never end there. But when you pull out your last trump, which is the spallation. Spallation can make everything which is lighter than the target. So why not try with spallation? So nature has shown in the universe it's being used. So let's go to a place which has similar proton energy spectrum, like 1 GeV order of, and that is CERN. Obviously, you all know the LHC, which needs very high energies. But since those are synchrotrons, and a synchrotron is efficient in accelerating by a factor 10, 20, something like this, but not a factor 10 to the 3. It's like a car where you need a gearbox. So which means here you actually stack different synchrotrons in a line to reach the highest energy. And the smaller synchrotron can operate at a higher repetition rate, and from time to time it shoot some pulses, extra pulses on a fixed target, which is being used at Isolde 1.4 GeV. And you knock onto a target and you can make basically with different cross sections everything which is below. And in particular, which is just below, you have here the spallation channel, which is populating very efficiently isotopes. That is shown for lead. If you go now to something like tantalum, you would have here a very strong production in the range of neutron deficient terbium isotopes. Now it's a mess. You have many isotopes, so you must separate the mass to define the mass, and you use a laser ionization to define the element, and the combination of both gives you reasonably clean beams, which after some chemical post-purification can be injected into patients. This is the first clinical use of terbium-152 produced at Isolde, which was used for imaging of a patient in Bad Berka. Terbium-149 is also a very interesting isotope because it's an alpha emitter. Alphas, remember, very short range. So here we show the survival of mice which have been injected with some tumor cells which are growing. And you see here the survival time of the mice when they die or have to be killed because the tumor gets too big. And without treatment, the black curve, you see that the tumor in all mice before 40 days is becoming. You can now inject a small amount of this monoclonal antibody, which is this biological vector which can find the cancer cell and kind of hinder it in cloning. But if you inject a small quantity, nothing happens. There's no increase in survival. If you pump the mouse full with a lot of this antibody, it can delay the growth of the cancer, but eventually the cancer wins and the mice will die. If you take now the small quantity and give it small activity of this alpha emitter, then you can get a very good survival curve of 9% of the mice. And this terbium is very interesting because it's not only an alpha emitter, but also a positron emitter. So it's the only isotope which has a reasonable alpha and positron branching where you actually see where it goes and where it. And so those terbium isotopes have been pioneered mainly at the Isolde facility at CERN. And now to make it accessible more frequently, there was a dedicated irradiation position installed in the beam dump because with 1.4 GeV protons, they go through the primary target, they lose 100 or 200 MeV, but they are still useful to make spallation reactions. So one can at the same time put another target, irradiate it, and run it through an offline mass separator. And like this, you don't need to wait for the 1 week of terbium beam time, which is scheduled at Isolde every year, but you can make interesting radioisotopes many, many months while ever the CERN operates. Now, let's come to the conclusion how we can help to make new and interesting isotopes more easily available. Actually, this model is already in place in the US, that is the DOE isotope program. And they have gathered different facilities, which are national labs or university labs, which have special machines like high flux reactors or mass separation facility or special accelerators, linear accelerators, cyclotrons. And then they pool this know-how and competences. And when a user at some university requests a special isotope, which he cannot get commercially, he can get it delivered from one of the. It was always our dream to have a European equivalent to this. And this is the so-called PRISMA project, which has started last year. So it really gathers different facilities which have different competences. And here there are many marked, but not all are today already active. So there are some which want to work towards becoming an isotope producer in future and which joined the project to follow what kind of targets has to be developed and so on. So for example, the Grenoble or the reactor Jules Horowitz is not yet operating, will be, and so it's good to have them on board already. And this is the present portfolio of medical radionuclides which we are offering, and it's growing continuously. So we will present some new ones next week at our next collaboration meeting. So a user can go here, and that's a medical user. So a medical user is not used to work like nuclear physics people who go to across the world to make an experiment at RIKI. So they want to have a certain geographic coverage because things are short-lived, so it must be able to supply within a certain region. And depending on the type of isotope, we will require different types of capacity, reactors, cyclotrons, and so on. And not only this, if there's a very new isotope, it's very likely that the hospital which wants to try it out with some animals or so doesn't even have an authorization because it's something very exotic. Or they don't have an equipment to detect alphas or something which hinders to make the research. And therefore, we have 5 facilities where people can go locally to make use of a new isotope. So, for example, you can test new isotopes from CERN. You go just to Lausanne, which has a medical facility, or if you produce it in Denmark, you just go across the street to use it, or you do this in Belgium, or you get them in Polatom. So we have shown trying to make it very close so that we minimize decay losses of short-lived isotopes. And so that is the process how the users, which are here at the very end, are being served. So obviously we start with targets, which are irradiated with neutrons, protons, alphas. Then there's either mass separation process or chemical separation, both. Then you have to do the labeling, which means put the radioisotope into your chelator with the biological vector. You have to make characterization quality control, and then it has to be shipped either to the user facility, so you can be placed somewhere and you just get it delivered, or the user travels to this so-called medical facility. And that is again an interesting equivalence with astronomy, because in astronomy you have the classical visitor mode, where an astronomer travels to a special telescope to do his observations, which is common in many telescopes, especially smaller telescopes. But even for ESO telescopes, you have the visitor mode, where you can travel to Chile to do your observations. That is obviously the same in our fields, like here at ILL for neutron scattering, ESAF, it's the synchrotron facility, nuclear physics, PSI, GdR. And it is also like this in the so-called PRISMA PNA-free transnational access for medical facilities, where the people go and they make their cell culture or mouse or even patient experiments at such a facility. But then there is an orthogonal mode, which is a so-called service mode, which is often a very simple, very standardized method, where it's not effective to travel to the place. So, for example, ESO has the service mode operation, and there are simple neutron or X-ray experiments which can be operated like this. And one could imagine that should be a tool. So that you could imagine a TNA-free where you say, oh, please measure this before I come and do then the next. And finally, there is the service mode, which is not because very simple, because it's very complex. I mean, there's obviously for the telescope, no user will fly to Hubble or Webb to turn the telescope, and he would even not be allowed in the operation room to control the thing, not that it loses its orientation. Or in cryo-electron microscope, it's very specialized, so it's not the student who comes to check his sample who is allowed to touch it. And similarly, for the radioisotope production, it would take ages to get a training to be allowed to go into a nuclear reactor or in the target zone of a cyclotron. So here it's much better that it's the facility people who know how to operate it, to ship it out to the user. So to conclude, I have made an effort to find where there are some synergies between nuclear astrophysics and nuclear medicine. And very clear that first one is detection technologies. If you can develop a new detector which has some added value, it's most likely that you could find some application for nuclear medicine. Secondly, it's the production of the radionuclides. So special accelerators and high power targetry have often applications. Either you copy it and you have a separate machine which makes medical isotopes, or you can make new medical isotopes available. And we recently copied the very well-established transnational access systems of users like ENSA, ENSA2, Eurolabs. This has now an equivalence in the medical isotope sector, which did not exist before in Europe. But I make you also aware that there are certain anti-synergies or kind of competition, in particular with enriched isotopes. I showed you many examples where it's really the cost and the abundance of the isotopes which is a limiting factor. And the same isotope separators, which are separating calcium-48 for accelerator experiments at Grenoble or GSI. It's the very same machine which will make the ytterbium-176, which will be required more and more for making cancer treatment. So you can estimate already what will happen in the next year, who will be on the winning side. And that is an aspect which is being addressed with the so-called EURASIS initiative. So I think I came through roughly, and I open it now for discussion.